Welcome back. Before we get into eigenvalues and actually solving our first order system, we have to learn how to write this in matrix form and how to multiply matrices and add, multiply by a constant value. So we need to learn some matrix operations before we can get to that stuff. And later stuff, even after that, needs this stuff. So to write an equation in a matrix form, it's typically written in the form ax equals b. That's how you write the systems of equations. So by that, I'm going to rewrite this here as 3, -2, 2, -2 times x1, x2 is equal to x1 prime, x2 prime. The reason I'm able to write this like this, where this right here is a vector, and this is a matrix. When we're given a system like this, we want to solve for x1 and x2. Only problem with this current equation here is we don't have values for x1 prime and x2 prime, so can't solve it. But we'll get into that later. So for now, we're just going to focus on the basic properties. Why can't I write the system like this? Well, because of the way matrix properties work. So for multiplication, matrix multiplication, you multiply the row, well, actually, it'll be the row by the column, yeah. So the row of the first matrix by the column of the second. This is the, now, if you look at this one up here, to rewrite this in this form up here, we have to multiply the row of the first matrix by the column of the second matrix. In this case, it's a vector, but so that would be 3 times x1. Let me write this in orange. 3 times x1 minus 2 times x2 is equal to x1 prime. See that? I just multiplied this by this, and this by this. And you set it equal to this right here. Now for the next one, you do this times this. So with the row, so you go this way here. You go this way in your order of multiplication. So it's 2 times x1 minus 2 times x2 is equal to x2 prime. Right? That's how you do matrix multiplication. There's some rules to this though. So rules, number 1. I have them written over here somewhere. So I can just copy down what it says. Here it is. So yeah, so the number of rows in the first matrix that does not look like first. Number of rows in the first matrix. Oh, sorry. I mixed this up. It should be columns. Number of columns in the first matrix has to be the same as the number of rows in the second. So if we have a matrix like this, and we multiply it by something like this, is this possible? Think about it. Are the number of columns in the first matrix the same as the number of rows in the second? You would say yes, correct? Because look, you have how many columns in the first matrix? 1, 2, let me get my pointer. 1, 2, 3 columns. Now in the second matrix, how many rows do we have? 1, 2, 3. It would work for any vector of size that looks like this. It can be just this portion right here would work. This whole thing right here would work. Or if we add another row onto here. Actually, we can add infinite amount of rows onto here, and it would work. Would be good. Let's say we have something like this. We multiply them together, and well, then we have something like this. We now have 3 columns, 1, 2, 3. We only have 2 rows. So this, not good. We don't want that. So there's a few more rules to matrix multiplication. Say for this first example here, what if we reverse the order? Well, first of all, if we reverse the order on this one, on the one that we have right here, if this was 2, 1, 1, negative 1, 2, negative 1, suddenly this is no longer possible because the number of columns is only 2 on the first one. This is 1, 2, and the rows is 3. That's no longer possible. So you can see it's completely different. Even if this one, if I were to make this a cubed matrix, so if I add a column onto here, where's the example? Negative 1. My eraser's not working. Here it is. Negative 1, 0, 1. This is not the same as what was up here. It's not the same as that. You would get completely different answers. Let's call this one here matrix A. Let's call this one here matrix B. If we were to multiply A times B, that would be 2, 1, negative 1, 1, negative 1, 0, 2, negative 1, 1. Oh, I just did that backwards. That's B, sorry. 1, negative 2, 1, 0, 2, negative 1, 2, 1, 1. How would we get the answer to this question? So A times B, what would we do? So we first look at the first row and then the first column that corresponds. Okay, so then we would do 1 times 2 is 2. Oh, right, sorry. And then you would, so, okay, this is interesting. I did not explain this before. So when you do this multiplication of a larger matrix, when this is more than 3, when this is more than 1 column, you have to add up the sum of all of these in here. So you do 1 times 2 plus negative 2 times 1 plus 1 times 2, and that goes in this spot right here. So it would be 1 times 2 minus 2 plus 2. All in this top left corner here. Now in the middle, we will look at this one here and add them up. So we would have 1 times 1 plus 2 minus 1 let me do this so you can easily see the sections that I'm making here. They're kind of close together. Okay. We have the last one will be 1 times -1. That's -1, 0 plus 1. Let's go down to the next one. Now we look at this row and the same columns. So let's multiply the second row by the first column. That's 0 plus 2 minus 2. And then we have second column, second row times the second column is 0, -2, +1. We have 2, and then the last column there is 0 times 0 plus 0, then -1 times 1, -1. Now we're going to look at the last row times each column. So the first position is 2 times 2 is 4, plus 1 plus 2, and then we have 2 minus 1 minus 1, and then we have -1 plus 1. So this becomes 2, 2, 0, 0, -1, -1, 7, yeah, 7, 0 again, and something's not right there. Oh yeah, because this should have been a -2. I multiplied that wrong. Sorry if I confused you on that. So that would be -1. So this is A times B. Now I'm not going to do it, but just to show you, if I were to do B times A, the answer would be 0, -3, 0, 1, -4, 2, 4, -5, 4, which is completely different than A times B. So as we can see, A times B is not equal to B times A. Now you can go ahead and do that out if you want to verify it. I don't want to waste up too much time on this video here because we have some more to do yet. So that's one matrix properties. They're not equal to each other. Another property is matrix multiplication satisfies the what's it called? I guess the associative law. So if you have A times B times C, you can multiply A times B. You can do those two first, and then you can multiply it by matrix C, but it has to be in this order though. It's no matter which ones you multiply, you can do A or B, or C times B, or sorry, I should say B times C to be correct here, and you get the same answer. So say you multiply these two first. As long as it's on the right side of the A, you would get the same answer as if you multiply these two first and leave the C on the right side, and then multiply those later. So you can do this first and then multiply by this, or do these first, multiply this by this, and you get the same answer. So that's one law. And it also satisfies the distributive law. So if you have a matrix on the outside, let's say a sum of matrices, which we'll get into in a minute here. This is the same thing as, you just distribute the A into both of them, and it's A times C, right? And this leads us into matrix addition. Actually, before I do that really quick, let me show you multiplication by number. Say we have some number alpha on the outside of A. That's the same thing. Say we have a vector of A, B, C, not a vector matrix, sorry, D, E, F, G, H, I. Might as well do lowercase. If we have this, that's the same thing as writing alpha times this. That would be equal to alpha A, alpha B, alpha C, alpha D, alpha E, alpha F, and you get the idea. You multiply every index in the matrix by alpha. Every single entry. So that would, if you're doing the same property up here, the distributive law, it'd be the same thing. That's just that there, right? Say you had two different ones, so like alpha and beta, for example, and you multiply it by A. That's the same thing as adding two different matrices, one that's multiplied by alpha and one that's multiplied by beta. That's all. So now this takes us into matrix addition properties. Let's see if I have any examples here that I can use. Okay, say we had the two matrices, A is equal to 1, negative 2, 0, 3, 2. I just came up with this. This stuff's not too bad. 3 times 4, negative 2, 3, negative 1, 5, 0, 6, 1, 2. Sorry if you can't read my handwriting. That's a 5. This is a 2. Okay. So, oh, sorry, this is supposed to be B, not multiplied yet. Okay, let's say we want to find out what 2A plus B is. Okay, so to do that, we would write, I'd prefer to write it out again. I'm just going to copy this down. It's easier than writing it all out again. It's the benefits of a tablet. Times B looks something like this. Oh, sorry, plus B. Not times, plus. First thing we have to do is we have to multiply the inside of the A by 2, right? So then this would become 2, and this is the property we just looked at up here with the alpha property. 2 times negative 4, 0, 6, 4, negative 2, negative 4, 2, 6. And then we still add this one here. Just might as well copy it. It should still be copied. Perfect. To add matrices, it's very simple. All you have to do, you add this one to this one, this one to this one, this one to this one, and you just sum up the same rows. And remember, these matrices have to be the same size. So we just sum up the indexes, I guess, for the constants. So this just becomes, this is very simple, right? 6 is probably the easiest thing we've done on this channel. We're just doing addition. That's what, negative 4 minus 2, negative 6. 3, 5, 9, negative 2, 2, 3, 8. That's it. Right, so that's that. And you can add these in either order. As you can see, if you flip them around, you get the same answer. Not the same for multiplication. If you can't multiply, you can't. 8 times B is not the same as B times A, as we've been over. So that's addition, pretty straightforward. It also, as you know, it wouldn't matter for addition if you add them. So as I just said, this is the same thing. Another thing that would be the same thing is if you add B plus C first, or if you add A plus B first. It doesn't matter what order you go in. You can completely flip them around even. You could do C plus B plus A. That's the same thing as A plus B plus C. And you can do these two first, or you can do yeah, that's the same thing. Right, or you can do these two first and you still get the same answer. Alright. That's multiplication. Subtraction is the exact same thing. It's exactly the same as addition, just, you know, you just subtract them instead of adding them. And we already looked at multiplication. And so that's really it for this. Is there anything else? Let me see. Oh, you know what? Yes, I'll include this stuff in this video. So we have something called the, oh, hold on. What is that? Yes, I want to look at the transpose of a matrix. So let's take a look at this one here. Our A matrix. So we'll call this matrix transposition. So this is A. So typically you'll see it written as either A prime or A with a T here. I think, you know, if you're familiar with MATLAB, prime is used in MATLAB for inverse. Sorry, yeah, not for inverse, for transposing a matrix. So all it does when you transpose a matrix, you interchange the rows and columns of the matrix. So A transpose, you would just you would take this. Let me see. You take this row here, and you would put it here. You would take this row here, and you would put it here, and you take this row, and you'd put it here. So that's all you do. So you just make the rows into columns, is the way I think of it. So you would have negative, so you have 1, -2, 0, 3, 2, -1, and -2, 1, 3. It's almost like you take the matrix, what's my thing? Take the matrix and you kind of think of turning it this way. Almost like you rotate it and then you flip the rows. That's one other way. That's kind of overcomplicated. What am I talking about? Yeah, you just turn the rows into columns. That's how I think of it. That's how you transpose a matrix. Pretty cool stuff. So that's the transpose of this matrix. Sorry, that should be AT. And the last but not least, I want to cover the identity matrix. Let me find it here. Yes. So the identity matrix is if, say you take, I can actually show you this really quick as well. Say this is A. Let's take our A back here. I'll show you something really cool. Well, actually, oh, this is kind of rough because I never explained inverse yet. You know what? I will leave this for the next video. I will briefly introduce it, but I will be a little hand wavy. I promise you, I'll prove the inverse matrix, the identity matrix in the next video. So here we have the identity matrix. Oh, that's. It's defined as I is the definition that you'll see everywhere for the identity matrix. And it follows the form 1, 0, 0, 0, 1, 0, 0, 0, 1. And if you keep going, and you know, you can keep going this way or down this way. You get the idea. But this is the identity matrix for an n by n system. So if you know A up here, so you know, I'm not gonna get too much into the specifics here, but if we had A times its inverse, which I'll get into in the next video, that is equal to the identity matrix. And it actually is quite interesting. If we flip that, it's the same thing. I know we said that this is the cool property about the identity matrix. So this basically tells us, it changes the rules of it kind of changes the rules where we can have A times B is equal to B times A. This only works and where B is the inverse of A. I know that was kind of redundant to the last step, but you'll see where I'm going with this. So the reason why we do this is because this only works if the matrix A is non-singular. Otherwise known as invertible. Matrices that cannot be inverted it is called singular. I'll get more into this in the next video, but this helps us, move some matrices around. As long as the matrix A is invertible, it can be said that times its inverse is equal to the identity matrix. And we will get into this. This is how we solve for. I shouldn't have did this in this video, but this is like a little preview to the next video. Basically, another property. Well, what happened? Another property. If you take A times I, the identity matrix, set it equal to I times A, that is equal to the matrix A. So that's kind of helps you understand probably this up here, right? Because if you look at this, I kind of skipped ahead. That's my fault. If you look ahead, this is A times, well, think about it this way. Let's look at this right here. If this is equal to A, right? Because it is. This is equal to A. You're multiplying, well, not exactly. Then if you rewrite this, when you divide, divide by a matrix, you kind of think about it as you take the inverse. So you multiply it by this inverse here. It's quite interesting. But this is how we get into the inverse stuff, which I will go over in the next video. So hope you enjoyed this video. We went over multiplication, basic stuff, addition down here, some scalar multiplication into matrices, some addition here, and then the transpose of a matrix. You just multiply, sorry, not multiply, you just change the rows into columns. You just interchange them. The identity matrix we went over. We went over the basic identity property here, right here, and then we showed that we can define some matrix A inverse times itself is the identity matrix if A is not singular, which I'll get into what that means in the next video. So I'll see you for the next video for inverse matrices.